Here's the key idea. This is what you have on your first line. Static charge is produced by electron transfer. That's what you can write at the top of the notes on the very, very first line. That's the key idea of the next while. Once again, just like in chemistry, Riley, all the action is with the electrons. It really is. In fact, there's a reason we call it electricity, and it's because it's the electrons that are moving through the wires. I wrote down here, draw a simple model. Oh, a picture of lightning. We're going to look at that. Before we start learning about electricity, we need to review what an atom is. So in your notes it says, draw a simple Bohr model of an atom. So let's do that right here. So let's do what do we call the thing in the middle? It begins with the letter N. Okay, let's draw a big nucleus, kind of exaggerated. What's inside the nucleus of an atom? There's two particles, two subatomic particles. Sorry? Protons and electrons, I disagree with. Okay, protons and neutrons. So let's go P plus, and let's go N0, N0. We'll just put 2 just to show that, okay, here's inside the nucleus are protons and neutrons. What's outside the nucleus in shells? Electrons. So let's go D, and let's put a little E minus there, little E minus there. In fact, this is, I think this is a helium atom. Does helium have 2 neutrons? Yeah, there's a helium atom. 2 protons, 2 neutrons in the nucleus, and 2 electrons. We could do more. But what I want you to notice is location, location, location. Aiden, where are the protons and the neutrons located? In the nucleus. Where are the electrons located? Which ones are easier to access? The electrons. There's a reason why electricity is all about the electrons. I copied and pasted a bigger, more pretty diagram, and here's the question I wanted to ask. Which type of particle would be easiest to move? What do you think? Aiden, you answered this question already. Those are the easiest to move, locked inside the nucleus, tough to get at. Why? Outside, yeah, it's really that easy, okay? Which type of particle would be easiest to move? The electrons. So in your notes, you can write down you can write the word electron, or of course we have a lovely symbol, the E minus. The electron is the easiest to remove because it's on the outside of the atom. Far easier to remove than you realize. You can remove them by rubbing. You can remove them by rubbing. That's all that's happening when you rub a balloon on your hair to make it stick to a wall. All you've done is you've rubbed electrons from you onto the balloon. So ready? We've got a short lab. If you look just below that big box that I drew in your notes, guys with me? Back to our notes, Taya? Need you here. I know it's a distraction. You can handle it. I want you back to the notes now. If you look just below where we drew the Bohr diagram of an atom, it says this. There are 2 types of charge. And I wrote plus and minus. When I write plus, what English word am I really trying to get you to say? Yep. Positive, and you can use plus for positive and you can use minus for negative. Omid, you with me? Put that away, kiddo. So it says there are 2 types of charge. Fill this in. Figure out where we are. In the notes, second line below the big box there, plus and minus, positive and negative. And in matter, the positive charges are basically fixed. Turns out only the negative can move. We can, with fancy technology, Omid, now move protons around, but it took splitting the atom and particle accelerators and stuff like that. Moving electrons is as simple as a piece of tape on another piece of tape yanking it off. I have in your notes, draw a neutrally charged object. A neutrally charged object has the same number of positives and negatives. And what we're going to be doing, Tristan, is we're going to be using what are called charge drawings. We can't actually draw the total number of protons and electrons because there's trillions of them. But you know what? I'm going to say, to show that this little piece of metal that I've drawn here is neutral, I'll put 1, 2, 3, 4, 5 pluses. If it's neutral, if I put 5 pluses, how many negative charges must it also have? So go 1, 2, 3, 4, 5. Aiden, if you did 4 pluses and 4 minuses and you said that was neutral, I'd take that. If you got really artistic and you did like 15 pluses and 15 minuses, I'd take that. Usually I draw 4 or 5. A neutrally charged object actually has several trillion protons, positives, and several trillion electrons, but it turns out they have about the same number. So we show it that way. And the word for that, equal number of protons and neutrons, you can underline it at the bottom of the page, is neutral. Then you can turn the page. So when we pull off the top tape, it takes some of the electrons from the bottom tape. So the top tape has extra minus, extra negatives, extra electrons. The bottom tape has extra plus, has fewer electrons, and fewer electrons, Amelia, automatically means you're more positive. You weren't foolish looking at your phone or anything like that, were you? If I wanted to draw this as a picture, I might go something like this, Hudson. I might say, you know what? I'll give the top one 4 pluses. I'll give the bottom one 4 pluses. I'll start out that way. And then to show that the top has extra electrons, maybe I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And on that's got more electrons than protons. And I want you to realize, Kyle, when I say something is negatively charged, I'm not saying it has no protons. That's impossible, because all matter has protons, has positives. I'm just saying it's got more negatives. So that top one, it's got a few positives, more negatives, it's negatively charged. The bottom one, you know what? I'll give it a couple of electrons, but I'll give it some more positives. It has a net positive charge. If you gain electrons, Omid, you have a negative charge. So this is in your notes as well. If you gain electrons, negative charge. If you lose electrons, positive charge. So far, so good? So on your test, I already talked about that. Probably at least once or twice, Matteo, I'll ask you to draw a charge diagram. I'll say, draw me a picture of something that's got a negative charge. You can make them all negative. I won't take marks off. But as a science nerd, I always tend to emphasize, look, it's got some positives, but more negatives. Or if I say draw something that's positively charged, Aiden, you can fill it with pluses, and I'll give you full marks. But as a science nerd, I'll always put a couple of minuses in there. So, look, it's got some electrons, just fewer than the number of protons. Is that okay? It's me being fussy. Many objects that we use today have neutral charge. Pen, balloons. But you learn as a little kid, it is possible to charge them by rubbing. It's possible to charge them by rubbing. I have here in my notes, Versorium Lab. We're actually going to do this one later. So keep going in our notes. Static charge. Here is the key idea. When electrons build up on a material, it becomes, the word we use for it is charged. This charge is called static because it's not moving. If we want it to move, we have to send it through metal wires. But static charge means you've got a bunch of electrons all clumped up and they're stuck there, but they want to go somewhere. Why do they want to go somewhere? Because they repel each other. In fact, this brings us to our key idea. Charges build up through friction. For example, when you take stuff out of the dryer, you may notice some of your clothing clings to other clothing. That's because rubbing back and forth in the dryer has generated static cling. Also through friction, through Nicole's wonderful demonstration here, we have that balloon still sticking to the wall. Wow. Okay? What happens when you give someone a shock? What do you think lightning is? We'll talk about that. Put your pencils down. I've explained to you then how a car protects you, and we'll talk about it now in more detail. Here's the key idea. If you want to memorize any three things, in fact, after these three rules, I could give you the test tomorrow technically, because all of it's going to come out of these three rules. The key idea in electricity, which is at the bottom of the second page, you want to fill this in. Like charges repel, unlike charges attract. You cannot get these mixed up. Now, there's a third one, a little more obscure. Neutral charges, like the wall, are attracted to either negative or positive charges. The balloon was negatively charged, the wall is neutral, but you can see they're attracted to each other. It's still going. Nicole put a good charge on there. You're shocking. Okay? Why are neutral charges attracted to both? Put your pencils down, look up. Where's my balloon? Here we go. So let's look at what's going on with that balloon. Kev, you're not foolishly looking at your phone again or anything like that, are you? Guys, put them away. Put them away. So here is Nicole's sweater and the balloon. So when I rubbed it onto Nicole's sweater, it picked up some extra electrons. See it? Okay. Now, look at the wall. It's neutral. How can you tell? It's got about the same number of protons and the same number of electrons. Which ones are free to move around? Watch what happens. These electrons, as they get, watch the wall, watch the wall, watch the wall. Notice what's happening to the electrons in the wall as the electrons in the balloon get closer. What's happening to the electrons in the wall? Which means the very edge of the wall is now charged which way? It's a net positive. And the balloon is? So that's why in a neutral object, if you bring a charged object towards it, actually inside that neutral object, the electrons will move away and the positives will stay. Or if it's a positive, the electrons will move towards and the positives will move away. And so you actually get a small charged area in the neutral object. In the neutral object. Why? The electrons inside a neutral object move around, leaving part of it charged. So if you bring a positively charged object towards something that's neutral, they'll be attracted. If you bring a negatively charged object towards something that's neutral, they'll be attracted. That's the explanation. I'm assuming all of you at least once have rubbed a balloon in your hair and stuck it to a wall or a ceiling. That's what's going on there. Okay? So I wrote down here balloons and static electricity simulator. I showed you that. But now we need to talk about witchcraft. We need to talk about why, when you had those two pieces of tape and they were either repelling or they were attracted, why that wasn't witchcraft. It turns out in physics, we have something that we call action at a distance. Riley, you watch Star Wars? Do you know the basic plot or the idea behind Star Wars? And you watch Star Wars. In Star Wars, there's something they talk about. It's may the blank be with you. They have something, this mythical thing in Star Wars that they call the Force. And one of the things that the Force allows Yoda to do from a distance is to cause things to move. In physics, we say that's impossible. That's witchcraft. You cannot move something without touching it. In fact, the phrase we use is we say, you can't have action at a distance. Wait a minute, Mr. Dueck. I was moving those pieces of tape without them touching. You were touching them. No, Mr. Dueck, I don't think I was. You were touching them, but you were touching them with something invisible called an electric field. Watch. Okay, so here is a closed area, and I'm going to put a charge there. And this charge is a negative charge. The reason I know is I set this up earlier. I'm going to put another negative charge there. What do these two negatives do? Attract or repel? See it? In fact, let's move this guy really, really close. I'll press pause. If I hit play, what will these two negatives do to each other? Repel. You know what? I'm going to add a, instead of a charge that's negative, I'll make a charge that's positive. See if you can figure out, I'll mix these up. See if you can figure out which one is positive, left, right, or bottom, by the way they behave. Okay? This is what's going on, this little dance at a subatomic level all the time when you have positives and negatives. Opposites attract, like charges repel. Back to our notes. So I wrote down here, reading check, page 251. Did I cleverly copy it? No, I didn't. I'm going to open it up in a second. It says, take turns asking your lab partner the questions and answering them out loud. You have 5 minutes. This will take us close to the tone. You're not going to have any homework yet. We're going to finish this. But can you turn to page 251? If there's 3 of you, you'll take turns. It's page 251. One of you has to have a textbook. $251. Does Omid have one?
No.
No? I want mine back.
Also,
Hang on, let me see. Hang on, I'm still videoing.